So what we're going to discuss in this video is the derivative of two of the simplest transcendental functions. We're going to start with the trig functions, and of course, therefore, we're going to start with sine and cosine. So we're going to do a full analysis of these two, and then in another video, we'll talk about the rest of the trig functions. So what do we got here? Well, y equals sine of x. Well, here's the way we're going to look at this. Let's look at a graph. So I've got the sine function. So let me just actually, boom, 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 roughly equal. We'll say this is 1 and that is -1. All right, so I'm going to sketch myself a sine graph. Doesn't have to be perfect. It just has to be. There you go. I'm just going to do one cycle of the sine graph. Oof, not my best sine graph function. So this is y, this is x, and obviously then this is pi over 2. This is pi. This is 3 pi over 2, and this is 2 pi, 1 and -1. So remember the derivative graph. So if this is f of x, the graph f prime of x, boom. I just want to make sure I have the same spacings roughly, boom. The derivative graph has to be the graph of the slope of this function at each point. So let's put in some of the easiest points there. And I think you'd agree with me that one easy point we can talk about is pi over 2. Because at pi over 2, the slope is clearly 0. And at 3 pi over 2, the slope is clearly 0. Great. Now, let's talk here. This might be hard to see because I've only drawn one cycle, so I'm just going to kind of like sketch in what's happening here and sketch in what's happening there. Because I want to talk about what's happening at 0. So the first thing I want to note at 0 is that the slope is positive. So there's some positive value that the slope has achieved. Okay? Now, notice here that this is not only just a positive value, it's a maximum positive value. Because you can see this slope gets steeper and then gets less steep. Same thing here. It's getting steeper, then it's getting less steep. So whatever this value is, it is a maximum positive value. So when it looks like this, that's true over here as well, I've got that same maximum positive value. Now, notice here I've got a maximum negative value. So what I know about the sine function is that the sine function has symmetry. And because it has symmetry, I can then lean on that symmetry knowledge to say whatever this maximum positive value is, that this is a negative value that has the same magnitude. So I'm just going to put that in. Now, I don't know what magnitude that is because I don't know what the slopes are at those points. I just know that this is as steep as this, but this is positive steep and that's negative steep. So there I go. So I've got this. But now, how do I connect the points? Right? Do I do like the Charlie Brown t-shirt? Well, remember that this is the graph of the slope of this function. So if we look at what's happening to the slope of this function, the slope of this function in this section of the domain, let's say like the first half of this domain, I would argue that this slope is getting less steep, but it doesn't really get all that much less steep in the first half of the domain. And it goes from positive, that max positive, down to 0 pretty quickly in the second half. So that means the value of the slope maintains a large positive value and then it dives down to 0. So it's not linear, right? Same thing here. In this section of the domain, there's a lot of change. We're going from 0 down to some negative number, and then from here to here, it kind of maintains that large negative value. So that means that there's a big change in the slope to negative values and then not as much. And then I'm going to lean on that symmetry in order to give us the rest of the graph. So there you go. Now, once again, I haven't proven anything. This is just observational, understanding what the derivative means. The derivative function as a function that describes the slope of the original function at every point in its domain. So we all kind of know where this is going, right? but still, it bears thinking about these things in the right way. So if we look at this, and I had to take a guess what this is, well, it just looks like a cosine graph. Absolutely it does. I don't know what the amplitude of that cosine graph is. I mean, like, I could do some actual numbers here in order to figure it out, but there's nothing about the analysis that I've just done that tells me that this is anything specific. It could be 1, it could be whatever. Now we all know it's 1, but like, let's just put that out. What I think is really interesting here, hopefully you do as well, is that I have a periodic function. And the period of this function, or the frequency of this function, is 1, right? Like the period here is this amount here, this 2 pi amount. Notice that this graph here, the cosine graph, has the same periodicity as the sine graph. So I'm just going to write down as a question, does the derivative of a periodic function always have the same, what's called periodicity of the original function? And that's going to be an active question, because certainly that's true in this case. But let's see if we can make an argument as we go through this to develop a fuller sense of it. So there we go. So far so good? All right, cool. But now let's prove it. So for proving it, folks, what does that mean? Well, that means the only way to prove the derivative of something is to do the definition of the derivative. So here we go. The definition of the derivative, that says dy dx is equal to, and just to remind us, you wouldn't have to write this step, but the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Okay, you could skip that step and just go right to the first plug-in. So the limit as delta x approaches 0 of sine of x plus delta x minus sine of x all over delta x. Clearly, if I plug in 0 here, I get an indeterminate form because I have 0 over 0, because this becomes sine of x minus sine of x over 0, and that would be 0 over 0. Which means that I need to do something in order to transform this function in order to do this problem. Well, what transformation can we do here? Well, what's staring at us in the face is right here. I've got a trig identity. So I'm going to use the trig identity in order to expand that. So oftentimes we're going to expand things before we do anything else. It might seem weird to make the problem more complicated, but oftentimes it gives you more options, right? And that's my option here. So sine of a plus b is sine of a cosine of b plus sine of b cosine of a. So that gives us sine of x cosine of delta x plus sine of delta x cosine of x, and then minus sine of x all over delta x. All right, so what am I going to do with that? Well, after we expand, oftentimes what we want to do is regroup. And so what we need here is a regrouping principle. Like, what are we going to group by? And there's a lot of grouping principles here. I could group by the delta x's terms, right? But that's kind of actually how I have it, is the first two terms have delta x's, the last term doesn't have a delta x in it. That was our original grouping, so I don't want to do that. So what I'm going to do instead here is I'm going to group by, I have some terms that have sine of x and some terms that have cosine of x. So let's do that regrouping here. So the limit as delta x approaches 0 of sine of x, parentheses, let's say I've got a cosine of delta x minus 1 plus cosine of x times the sine of delta x. And all of this is over delta x. All right, so how does that help us? Well, here's where we can remember a special property of the limit. The limit distributes across addition, right? Remember that the limit of the addition of two functions is the same thing as the addition of the limit of two functions. So what I'm going to do here is I'm going to distribute that limit across this addition, because now what I have here is sine of x, and I'm just going to like write this a little bit differently, okay? Because here's all my delta x terms, here's my non-delta x term, plus the limit of delta x approaches 0 of cosine of x, and then I've got sine of delta x over delta x, right? Now, here's an interesting thing. Notice this operation only acts on terms of delta x. Sine of x and cosine of x are not functions of delta x, they're functions of x, meaning that this operation sees these two things as constants. So what does that mean? It means I can pull them through the limit operation, and the limit operation doesn't affect them whatsoever. So now, what do I do with this? Because I am left with, unfortunately, two limits where if I were to plug in, I would get indeterminate forms. Now, some of you are screaming to yourself, I know what those limits are, we did them before, but not in this class. So, if you don't know how to do this, what is our option? Got it. Our option here must be, when I have a limit I don't know how to do, my brute force methodology is that I am going to do numerical evaluation. So we're going to do the numerical evaluation of each of these limits. And once we've got it done, then we have it. But we do need to do that. So here we go. Let's do the first one. We got the limit as delta x approaches 0 of cosine of delta x minus 1 over delta x. So here we go. Here's my x. Here's my little f of x for this thing, which is going to be, actually I don't want to use fx because we know what fx is sine of x. Cosine of delta x minus 1 over delta x. That's what my table is. And I'm going to use variables of negative 0.1, negative 0.05, negative 0.01, 0.01, 0.05, and 0.1. Now, it's important that when we do this, that we have our calculators in radian mode, because that's what the expectation is here. So here we go. You can stop me from talking on this video or speed me up and put this all in your calculator, but you should try this, and then we'll come back and have some values. Okay. Okay, so this is 0.04996. Cosine of negative 0.05 minus 1. Okay. Cosine of 5 1 divided by, okay, I'm getting 0.02499 cosine negative 0.01. Okay. And this is going to be 0.00499 going out. Okay, great. So there we go. And then what do we have here on the other side? just knowing how the cosine function, that these two things are going to have the same magnitude, just the same sign, but because in the denominator that we won't be canceling out the negative there, these just flip in terms of numbers. All right. So I think it is pretty obvious what's happening here. As we approach from the left, this approaches 0. As we approach from the right, this approaches 0 as well. Therefore, we can say the limit as delta x approaches 0 of cosine of delta x minus 1 over delta x is equal to 0 because we're approaching the same value. Well, that's pretty handy there. So now x, and do the same thing for sine of delta x. Actually, this should be delta x. Oof. Delta x over sine of delta x. Sine of delta x over delta x. Okay, so let's take the moment and just do this here. Okay, this one's a little bit simpler to plug into the calculator. Right, I've got 0.9983. Okay, sine of. Now in your calculus classes, folks, you will go through some different derivations of this. I will say the words squeeze theorem is something that you might hear as you're doing this. I will leave that to your calculus teachers to talk about because they want to prove things in a different way than we're proving things, to a different level of rigor. I am doing this numerical evaluation, which technically does not have the same rigor as what their solutions would be, but there you go. And this has, once again, symmetry and values, so there we go. So what's happening here as it's approaching, it goes to 1, and this goes to 1. So the limit as delta x approaches 0 of sine of delta x over delta x is equal to 1. Those are some nice and handy things to have in the pocket. So now we can come back up this way and go, okay, well, this went to 0 and this went to 1. Oh, okay, cosine of x. Done. Therefore, we can now make a new derivative rule. This is the derivative with respect to x of sine of x is equal to cosine of x. Box it, memorize it. It's our first transcendental derivative rule. All right, so I was going to do the cosine in this video, but I think I've already talked too long here. We'll leave the cosine for the next video, as well as the rest of the trigonometric functions.